All right, so this is going to be a quick introduction to uh, chapter 5.1, proof by induction. Um, we are thinking about the idea of how we want to prove statements that are going to be true for all n, or for all positive integers. It's often difficult, if not completely impossible, to show that statements such as this one, right, for all n p of n, are true by directly showing it for every possible n, right? Sometimes we can do the things we were doing, like, for all n, if, n is odd, then n plus 1 is even, right? That one we can show directly. But there are many proofs that we've talked about, and there are many other times in computer science and mathematics where you cannot directly show this, right? So what we can do is we want to show that it is true for one, and then if it is true for any number, it is also true for that number plus one. This idea is called proof by induction, right? So mathematical induction is a proof technique that we can use to prove statements that assert that P of n is true for all positive integers n, where P of n is a propositional function, right? So an induction proof has two parts, right? We have the basis step. The basis step shows that P of 1 is true, right? This statement is true when n equals 1. And then we have the inductive step. We show that the conditional statement P of k implies pk plus 1 is true for all positive integers k. So what's happening here is that we are saying, okay, well, it's true for 1, right? So when n equals 1, this thing is true. And then past that, well, if it's true for any integer k, any positive integer k, then it's also going to be true for pk plus 1, right? That's the idea that, okay, well, if we show that it's true for p1, well, then that shows us, along with our induction step, then we show that it's true for p2. Well, then if it's true for p2, then we have that it's true for p3, and so on and so forth, right? So that's one of the ideas that's happening here, is we want to think about kind of almost like dominoes, right? It's kind of like a domino where you set them all up and then you knock the first one down, right? And the idea is coming from a mathematical idea that we can order all of the integers. There is a certain set ordering of the integers, and that's okay, right? And that's okay in that sense that it gives us those things. So if we want to talk about it in logical terms, we can talk about it as it's true, P of 1 is true, and for all k, P of k implies P of k plus 1. And if this is all true, then we have for all n, P of n, right? It's true for every possible positive integer. The assumption that P of k is true is called the inductive hypothesis, right? So this step here, this statement here, is called the inductive hypothesis. We're going to assume that if it is true, then it must also be true for k plus 1. So the nuance here is that in this induction step, you are not assuming that it must be true for all integers, right? You are not assuming that pk must be true for all integers. You're showing that if we assume it is true, then pk plus 1 must also be true, right? So then once you show that that is true, then you get that kind of domino situation I was talking about earlier, right? You can also start with a number other than 1 if you need to, right? Well, there's an example in your book that we will do later where we show that P of n is true for n greater than or equal to 4, right? It just kind of changes where your dominoes start, right? It doesn't change anything about the proof. It just changes where the dominoes start. All right, so this is kind of the formal template for all of this that your book gives. And all of the examples that are given in your book follow this kind of step. And it's it's very formal mathematical language, but that is purposeful, right? It is so that we are cautious, so that we make sure that we check all the boxes that we need to check, and we do all the things we want to do, right? So our first step is that we need to express our statement in the form of for all n greater than or equal to b, p of n. So remember, this is our propositional statement, P of n. This is a statement that can be true or false. Think back to chapter 1, where we learned what these propositional statements are. And this is for an integer b. If you want to show that P of n is true for all positive integers n, then you have that b is 1. If you want to show that P of n is true for all non-negative integers n, then b is 0. Right? If you want to show that it's true for all positive integers greater than 4, then b is 4. When we're making our own conjectures and our own proofs, you may need to look around for some small values of b and test it on certain things, just to kind of see what b should be. Right? So your first part is going to be titled the basis step. And in that step, you are going to show that P of b is true, right? That will probably be that P of 1 is true or P of 0 is true. But again, B can be separate. It can be different if you need it to be. You're going to title your second part as the inductive step and state the inductive hypothesis, right? So this has the form, assume P of k is true for an arbitrary fixed integer k greater than or equal to b. The key here is that it's arbitrary. This is, again, meaning that if we show for any arbitrary k, then we can show that it is true for all k, which we've got here, right? So we've got our for all k, this is true. So if we can show that, then we get our induction hypothesis, right? We show these two steps and we get our result. So after we state our inductive hypothesis, assuming it is true, right? We assume that this is true. And then we need to essentially write out what pk plus 1 says, right? What needs to be proved using P of k. Then in the next step, we do that, right? We do exactly what we say we need to do. We prove that pk plus 1 is true by using k. This is often the hardest part, right? You want to choose the best proof strategy by looking ahead. How can you build on P of k? What kind of math do you need here, right? And then you want to identify your conclusion. Say this completes our inductive step. And then you want to state your conclusion, right? So by mathematical induction, P of n is true for all integers n with n greater than or equal to b. In our first example, we're going to prove that the sum of all integers from 1 to n is equal to n times n plus 1 over 2. Remember, we learned this in chapter 4 in our summations. It may have actually been chapter 3 in our summations. And now we are going to actually prove that that is true, right? So our basis step, well, we need to show that P of 1 is true. What is P of 1? P of 1 is that the sum of I equals 1 to 1 of I is equal to 1 times 1 plus 1 over 2, right? I'm subbing in 1 everywhere there is an n up here, right? And 1 times 1 plus 1 over 2 is equal to 1, right? And so the sum, that is the sum of all of the integers from 1 to 1 is 1. Sometimes the basis step is quite simple, right? But now we've shown that this is true for 1, right? The sum of the integers from 1 to 1 is 1 times 1 plus 1 over 2. Okay, so now for our inductive step, we want to assume this is true for pk. Right? So then what is our inductive hypothesis? What is the thing we are assuming is true? That the sum of I equals 1 to k of I is equal to k times k plus 1 over 2, right? And what are we trying to prove, right? Let's kind of make a note over here. Or let's make that smaller. What are we trying to prove? We're trying to prove that the sum of I equals 1 to k plus 1 of I is equal to k plus 1 times k plus 2 over 2, right? So what's happening here? We want to have our assumption that we have P of k is true, right? We are assuming, hey, this is true. We're good to go. We can use this. So if we are thinking about 1 plus 2 plus ... all the way up to k plus 1, we know that that is the sum of I equals 1 to k of I plus, separately, k plus 1, right? Because this itself is the sum that we're looking for earlier. Now, this is where we are using our inductive hypothesis. Under the inductive hypothesis, we know that this is equal to what? It is equal to k times k plus 1 over 2. That's our inductive hypothesis. Plus k plus 1. Right? Your book says that you should put an IH here over the equal sign to say that this, essentially imply that this is where you are putting in your inductive hypothesis. Right? So with a little bit of math, we can have that this is k times k plus 1 plus 2 times k plus 1 all over 2. All right, we're adding in our k plus 1 here. And then, with a little bit of math I am not going to do for you, you can do it yourself or look it up in the book. This is k plus 1 plus k plus 2, or times k plus 2 over 2, right? So from here then, we notice that we used our basis step and our inductive step, and we have completed our inductive step, and saying then that by mathematical induction, we have shown, spelled correctly, that the sum of I equals 1 to n of I equals n times n plus 1 over 2 for all n greater than or equal to 1. Right? So we started this on an easy one, right? We started this on an easy one thinking about, okay, well, their basis step, it was about the easiest thing to prove ever. And here, I think, and if you're not there, don't panic about it, but I think it is fairly easy to figure out where to sub in our inductive hypothesis here, right? Because if you're looking at the sum, if you're looking at this big sum, you notice this is the thing we already know, right? This is the thing that we are assuming that we know in our inductive hypothesis, right? So let's think about another one. Let's conjecture a formula for the sum of the first n positive odd integers. And then we want to prove it with mathematical induction, right? So for starters, we need to come up with a formula. We want to come up with a formula for the sum of the first n positive odd integers. Okay, let's think about that. So for n equals 1, we've got 1 equals 1. For n equals 2, we've got 1 plus 3 equals 4. For n equals 3, we've got 1 plus 3 plus 5 equals 9. Are you starting to see the pattern? We'll do a few more. 1 plus 3 plus 5 plus 7 is 16. For n equals 5, we got 1 plus 3 plus 5 plus 7 plus 9 equals 25. If you aren't seeing the pattern here, pause the video, give yourself a second to try and figure it out. But I will let you know that our conjecture, this pattern that we are seeing, is we are conjecturing that the sum of the first n positive odd integers is n squared, right? So this is 1 squared, this is 2 squared, this is 3 squared, 4 squared, and 5 squared, right? So the way that we can state this is that we have 1 plus 3 plus 5, do enough to establish your pattern, and then plus 2n minus 1, right? You'll notice that this is 2 times 5 minus 1. This is 2 times 4 minus 1. This is the way that we are going to, talk about our sequence. And we are saying that that we are positing is equal to n squared, right? So we want to prove that this is correct using mathematical induction, right? We want to consider our basis step. Our basis step is that P1 is true. Is P1 true? We've actually already done that. We've already shown that P1 is true. 1 equals 1 squared. Okay, so now our inductive step. For this one, we want to consider that this is true. Nope, sorry, not plus. If P of k is true, then P of k plus 1 is true, right? For all positive integers k. Right, so we assume our inductive hypothesis. Our inductive hypothesis, I will not use the shortcut. Is 1 plus 3 plus 5 plus all the way down to 2k minus 1 is equal to k squared. So now we got to do a little bit of math, and we need to think about what we want to do with pk plus 1, right? So our pk plus 1 starts with 1 plus 3 plus 5 plus all the way down to 2k minus 1 plus 2k plus 1, right? We add 2 every time, right? We're gapping 2 every time. So we go from 2k minus 1 to 2k plus 1. So if we're thinking about that, then similar to our previous, we know we've got our 1 plus 3 plus 5 plus all the way down to the 2k minus 1 plus 2k plus 1. And we know that our first piece is k squared by the inductive hypothesis, right? And then we have that k squared plus 2k plus 1. Cool. So what do we know? We know a little bit of algebra here. K plus 2k plus 1, which is equal to k plus 1 times k plus 1, k plus 1 squared, right? So here, what have we shown? We have shown that when p of k is true, we have, oops, that p of k plus 1 is true, right? Therefore, the sum of the first odd integers is n squared. 1 plus 3 plus 5 for all n greater than or equal to 1. Right? So you start with your basis step, then you have your inductive step, and then you state your conclusion. All right, so that's going to be the end of this video for now. I'll have another one where we work through an example or two.